OWAS very much for having me today. I'm from Linköping mostly, and going to Gothenburg is always very nice to meet all you folks here and security people here at OWASP. So thanks very much for having me. And my talk is going to be about hacking quantum cryptography. Very fancy title. We're going to have a bit of a relaxed talk about quantum computing, quantum cryptography, how to hack quantum cryptography. I mean, people say quantum cryptography is unhackable, but I hacked it, sorry. And then we're going to talk a bit about some cryptocurrencies and poke fun at them. I think that's always very fun to do here with you guys. So let's begin. So my name is Jonathan Jogenfors. I still haven't figured out how to pronounce it in English, but I guess Jogenfors is the Swedish way. I work as research manager at Secre Communications. I think some of you guys have met my former boss, Robin from Post. Now he's left Secre to do some other stuff. But I also work at Linköping University. I graduated with my PhD thesis in November. If you want to read more about some in-depth stuff about hacking quantum crypto, you can check my book. Just kidding. And I also work as a postdoctoral researcher at Linköping University. And of course, if you guys are interested in, I guess there are some students from Chalmers here, if you're interested in doing some master thesis work up with us in Linköping, either at university or at Secre, you're always very welcome. So, always described me as some kind of well-known researcher in cryptography. I don't know really why, because I would never heard about myself, but I don't know. So, Secre, we do cryptography and critical infrastructure. You can see our very modern fancy phone. It might not look like a modern touch screen phone, but it's a very secure phone. You can talk about real secret stuff on there. Also, Eternity is a top secret classified product. You can talk real secrets over there. But let's move on to the topic at hand. So, quantum computing. You probably heard about it because everyone talks about it, the threat of quantum computers. But what is it really? So, normally we have bits, of course, ones and zeros. You're all very used to them. In quantum computing, we have something called a qubit instead. It's not a 0, it's not a 1, but it's rather a superposition of both. So one qubit can be 0 or 1 at the same time. We call it a superposition. If we have two classical bits, now I know we can't point with this laser because no one can see it, but if we have two bits, we have 0, 0, 0, 1, 1, 0, or 1, 1. We can have 4 different combinations using 2 bits. But 2 qubits can be in these 4 positions simultaneously. So you can think, well, why can't we just model these qubits and write them down in a normal computer with bits and see what the probabilities of the positions are? Well, yes, we can do this, but the problem is it's exponentially growing. So if we have 3 bits, we can have 8 different positions. So it requires a lot more memory on a classical computer than on a quantum computer. If we were to have 50 qubits, we could model these 50 qubits on a classical computer, on a normal computer. The problem is we will need 2 to the power of 50 complex amplitudes to write down and store in memory. And that's impossible even for the largest supercomputer today. So with quantum computers, we can have exponential power in terms of, we can have qubits can store much more data than normal classical bits. But there are some myths and some problems, and I will talk about them shortly. Qubits can be constructed in several different ways. We do not have a working quantum computer today, but there are a number of proposals. We can have semiconductor quantum dots up in the top left corner. We can have semiconductor superconductor hybrids. We can have superconducting circuits. All of these are proposals that have been worked on for many years and can give us an idea of what can be possible in the future. You might also see Google has moved on towards quantum supremacy with 72-qubit computer. And you might say, well, 72 qubits, that's a lot of power, right? Well, the problem is these types of high qubit computers today aren't really general purpose. You know, in a normal computer, we will do Turing-complete stuff. It's like having a classical computer with 64 bits, 128 bits parallelism, but you cannot do everything with it. So quantum computers are still far away. We have to remember that they can do bad stuff to our cryptography. This has been a public service announcement. If you don't talk to your kids about quantum computing, someone else will. And the read the book says, quantum computing and consciousness are both weird and therefore equivalent. So quantum stuff is not a silver bullet, and that's what we will show here today. Many people think that quantum computers can solve everything by having lots of qubits and sort of exposing these qubits to a problem. And in an infinite parallelizable way, all these qubits will sort of magically give you the answer because they work exponentially in parallel. But this isn't really true, because qubits can only be worked on in some very specific ways. For instance, we have two algorithms, really, that we can use in quantum computers. Shor's algorithm, which is the real bad thing for us cryptographers, and also Grover's algorithms that does slightly faster database search than with a normal computer. Shor's algorithm gives us effective prime factoring. You know, in RSA, which is the big pub key crypto algorithm today, we use integer factoring as a problem. Two big primes, P and Q, we multiply them together. That can be done very fast. But then when we have the product n, it's very difficult, given just n, to find P and Q. This is the RSA problem. But Shor's algorithm can take this number n and effectively, we call it polynomial time, find these two factors, thereby breaking RSA. So this Shor algorithm will break RSA, it will break Diffie-Hellman, it will break elliptic curve cryptography. All our fancy public key crypto systems are essentially broken thanks to quantum computers. In theory, we don't have a working quantum computer yet. Maybe the NSA has, we can't be sure. But our symmetric crypto, AES, DES, well, it's not really safe anymore, is it? But symmetric crypto algorithms are safe as long as we double the key length due to Grover's algorithm. So it's not going from an exponentially difficult problem to an effective solution like Shor's, but it goes with a quadratic or cubic speedup. So in this picture, I have pictured 4 of the main quantum computing and quantum cryptography guys. To the right here we have Peter Shor, who's of course the author of Shor's algorithm from 1994. But maybe we can have these 3 guys on the left as our saviors. We have Arthur Eckert, we have Gilles Brassard, and we have Charlie Bennett. Anyone recognize those 3? So they are the inventors of quantum cryptography. Maybe quantum cryptography can save us because we want to have something public key when quantum computers do arrive. We need something that keeps our data secure. So how do we do this? Well, you guys have heard about the OneTime Pad. OneTime Pad is our unconditional secure. They're unbreakable. Basically just take our message, we take bitwise XOR with a key and get the ciphertext. And we can show that this cannot be broken in any way. Even if the attacker has no bounds, fastest computer ever, an infinitely fast computer, everything in this universe can be used by the attacker to attack the system, and it can still not be broken. That's why people think, oh, let's just use a OneTime Pad and we'll be safe forever. Well, OneTime Pads are difficult because you need a key that is as long as the message. You need a key that is random for every single bit. You can never, ever reuse the key. So often people fall into this trap of using a OneTime Pad system, but being broken by practical implementation. So you can see this OneTime Pad system here. The picture was used in the Cold War and in World War II. Famously, KGB spies used OTP to encrypt their communications back to Russia to tell Russian scientists how to make an atom bomb when they spied on the Manhattan Project. So OneTime Pads cannot really be used because they're too difficult to handle. We essentially changed the whole problem of encrypting our communications to transferring the key. We need couriers with big briefcases to travel around the world and give us OTP keys. But maybe we can do something different with quantum physics. So we can use physics to generate the OneTime Pad key. Essentially, the 5-second version of quantum key distribution or quantum cryptography is that we let quantum physics create a OneTime Pad key, and this will make quantum cryptography unbreakable. Here is a picture from our lab at Linköping University. It's a demonstrator. Our students taking the cryptography courses are allowed to work on this lab and try quantum cryptography for themselves. So if I had a working laser pointer, I could show you that in the middle we have a source. We call it a source because it's a laser that sends out photons to Alice and Bob. And Alice and Bob make measurements on these photons, and then they can generate keys from it. And importantly, the keys generated by Alice and Bob will be the same. So they randomly generate each a message, or a key I should say, and they're both the same between Alice and Bob. And they can be remotely located. Alice doesn't need to be close to Bob, and they can still get the same random and secret key. And they can generate as much key as they want. And then they can talk over the phone or over the internet and encrypt data with OneTime Pad and then make real secure messages. So how is this really secure? How does this work? Well, you guys know Heisenberg's uncertainty relation. So at home at the Heisenbergs, I can't find my keys. And then Werner Heisenberg says, you probably know too much about their momentum. Because, of course, Heisenberg's uncertainty relation tells us that if we know something if we know an object's position, for sure, we know nothing about its momentum, and vice versa. We cannot know both position and momentum at the same time, with high precision. This is one of the weird things about quantum physics. We can do the same thing with these photons. We can encode them in polarization bases. And then by measuring them in different ways, we can make sure that an eavesdropper will only introduce noise by trying to measure. Let's say that Eve cuts the laser beam or the optical fiber between the source device and, say, Bob. So here's the source device, and we have Eve, the eavesdropper, that cuts the fiber and tries to measure what is sent, and then tries to resend and tries to fake not being there. The problem is that Heisenberg then tells us that this polarization which it does will introduce noise. And Alice and Bob will then, when they talk later on and reconcile their bases, say, hey, there's too much noise on this channel. It's probably been eavesdropped on by Eve. So theoretically, we have unbreakable security here in quantum key distribution. This has been shown formally. We have papers here by Dominic Myers. This is like a 57-page paper and very, very technical, hard to read. I haven't read it myself, but newer papers have been brought up that are shorter and easier and tells us that as long as this noise rate is lower than 11%, then we can have unconditional security. Now, if you can't distinguish between noise, say, from bad detection or from a broken fiber or from Eve, so you have to abort if the transmission has more than 11% noise. But in theory, if we have perfect devices and are below this noise rate, then we have unconditional security. Perfect cryptography. Cannot be broken, even if you have a quantum computer, even if you have an infinitely fast computer, beyond quantum computers, anything. That's pretty cool. But 11% noise in the analog world, I mean, we are all mostly computer scientists and we're used to digital information, but in the analog world to have less than 11% noise, that's quite difficult. Because we cannot have repeater stations. We need line of sight communication for quantum key distribution. It's very difficult. So then how far can we send the information of a quantum cryptography? Well, the world record until recently was 144 kilometers. Pretty spectacular experiment done on the Canary Islands. We have two observatories, one on La Palma, which is Alice, and then Bob is on the island of Tenerife, and they each have access to an observatory, and you can see the cool green laser here between the two observatories. And they actually got quantum teleportation to work over this huge distance. Still, 144 kilometers isn't very far. I can't talk to my friend on the other side of the world using quantum key distribution, because we're still limited by line of sight. And sending it through an optical fiber is even worse, because fibers have attenuation as well. And without repeater station, it's going to be very difficult. But this experiment is really, really cool, and I recommend you check it out. So normally we use photons, and they're very fragile and difficult to control. It's a very image of a source device. You see a laser here, the blue part, splits into two, generating individual photons that we encode information onto, and then sent one to Alice and one to Bob. So how do we then break quantum key distribution? So this is the pioneer quantum hacker, my friend and colleague Vadim Makarov, works in Canada. This quantum state pirate device here. This is a Sidechannel Attack he's using, quite a cool little box. When he travels around the world with his machine, the customs officials ask him, hey, what's in your box? Like, can you bring this in? What is it? And it's like quantum hacking device. Because he's a Russian, he's the coolest guy ever. So how does this work? Well, I tell you about individual photons. They're hard to create, but they're also hard to measure. Let's say I send you a single photon. How do you measure it? Well, we have something called, sorry, I forgot the name, but we have specific devices that we can use that react to these photons in some way. They're not perfect, because they're limited by noise, and they have so-called dark counts. That means they will click even if no photon is coming in. There's a lot of electronic equipment in these devices that need to be carefully monitored and controlled. What Makarov showed was you can fool these devices, making side-channel attacks. I mean, 64 microwatts might not sound like much optical energy, but that's quite a lot of photons. And he was able to blind these detectors, sending in a continuous laser into them all the time, makes the regulator or the control system go haywire, and then this 647 level does not click, does not react, but the higher level 808, it does react. So you can see on the blue graph, the detector output never clicks, but then it always clicks for these two levels. So we can blind the detector. We can hide photons from coming in. And this we can use to fool Alice and Bob. I'll show you how. But first, this is the system we attacked. I cannot take credit for what Vadim has done. I talked about polarization. We send light with either this polarization or this polarization. The problem is that polarization is difficult to build in practice. If you have optical fibers, the polarization will drift around. If the sun shines on your fiber at day but not at night, you will need to compensate, because depending on the temperature of the fiber, it will be very difficult to control. Instead, these so-called Franson devices, they encode information onto time. So time is much more robust than polarization, because time doesn't really change when we send light through it. We can always measure the clocks, and they will stay the same. So we have a source device that sends photons to Alice and Bob, not with polarization, but we encode it at when it's being sent. And we have these mirrors and stuff on the left-hand side, on the right-hand side. I don't have so much to go into detail now, but we can attack this system. How? Well, imagine I flip a coin 1,000 times. I do it privately. I don't show you how it works, but I write it down every time. And then I tell you, well, I got heads 97% of the time. Okay, but wait a minute, I forgot to write down half of the flips. Sorry, my mistake, it's so bad. Can you tell that the coin is biased or not using this information? So I got 97% head, but never wrote down half of the events. Well, you can't tell, right? Because I forgot to write down half of my outcomes.
It's random, the ones you did not record.
That is a very good question. It depends on which ones I discarded. Exactly my point. How do you know which ones are discarded? Maybe I discarded almost all of the tails. Exactly here is the attack. So we hide the bad part, the noise. We hide it in what is discarded. You see, in the Franson quantum cryptography system, the system must discard half of the events. And by cleverly choosing how to send the data to it, we make it discard our noise instead of the data, thereby hiding our attack. Therefore, Alice and Bob will not notice our attack. You see, with unconditional security, Alice and Bob must be able to authenticate the source device. We replace the source with a Trojan horse. Normally, they should be able to detect it with these security tests in the system, but we hide that we're attacking it in this noise. So there's a lot more details in this, and some highly technical stuff, but let's just say we did an experiment at Stockholm University. Here we have the setup. We have a rack, 19-inch rack to the right with detectors, these single photon detectors. We blind them, and we also hide noise in the blinding. On the optical table here, you see those white boxes. We have our attack device. It has to be in these white polystyrene boxes because it's very temperature sensitive, and it will drift with polarization and drift in time unless we keep it very thermally invariant. Basically, we let Eve prescribe the key for Alice and Bob. Alice and Bob never noticed their attack, and therefore with Eve being able to choose the key, she will also know the message they send. So normally we have something called a bell value, And if the bell value is below 2, then it's insecure. The system does not pass the security test. We call this that the security fails. Above 2, however, security is okay. And we make the system believe that we are above 2, even though we're really not. But again, we hide the lower parts of this value in the noise. But the attack even went even further. We can do much more. Beyond 2.8 should never be achievable with quantum physics. If we are above 2.8, then Alice and Bob see, wait, this is some Star Trek stuff that's happening to our device. It shouldn't even be possible. It's like having teleportation or having some non-local correlations or whatever. We can even reach the blue line over there, 3.6, if we really want to. We shouldn't do this though as an attacker, because that will make Alice and Bob very, very confused. So we pull down our attack a little bit and stay at around 2.6. 2.6 will pass the security test. Still, Eve prescribes the key, breaking the system. Of course, you can make countermeasures to this. You can detect our optical blinding, but then we can just work around the optical blinding device, because a detector like that will also be susceptible to attack, and so on and so forth. So the bottom line for quantum key distribution is we basically have Schneer's law, but the quantum version of it. I like to say that any physicist can construct a quantum key distribution system that can be proved secure under some restrictions the physicist prefers. So this attack wasn't new when we published it. It's been basically known since 1998. But physicists, we like to get grants for our cool-looking optical experiment tables. It's expensive stuff, you need lots of staff to run it. And they realized, hey, we can call it quantum cryptography and do security stuff without having the security mindset, without thinking about what would an attacker actually do to our system. So eventually we had to publish an experimental paper and show this can really be done, guys. You need to be careful about this. You cannot use insecure systems with bad security proofs. So quantum key distribution is theoretically secure, but in practice, I'm very skeptical. Sidechannel attacks are very, very effective still, since we use single photons. And improper security proofs, like the system that discards half of the events, it's even easier to exploit. Quantum key distribution is not a silver bullet and will not solve our need for quantum safe cryptography. Instead, we have real work being done in the field of post-quantum cryptography. And now we have a problem here, a pedagogical problem. Quantum cryptography and post-quantum cryptography are two very, very different things, even though it sounds very similar. Post-quantum cryptography means making better cryptography algorithms that withstand attacks from a quantum computer. Quantum cryptography means buying lots of lasers and mirrors and polarization devices and building a physics lab and making cryptography with quantum physics. Two different things. You might know about the NIST competition, the same guys that certified AES. They're now making the post-quantum cryptography competition, if you will. It's currently ongoing. There's a meeting right now in Fort Lauderdale in Miami for the next round of submissions, and they have all these suggested versions for the competition, and they will now break them and see which ones will be good. And it will take a few more years, but hopefully we'll soon have good public key quantum safe cryptography again. Now, what else can we do with quantum physics? Well, we do actually have something we can see as nature's own DRM. In quantum physics, you cannot clone something. It's forbidden. Or I should say, if you have an unknown quantum qubit, a qubit, then you cannot copy it right away. We can copy outcomes, like if you have a 0, you can make 2 zeros out of it. If you have a 1, you can make 2 ones out of it. But if you have a superposition of a 0 and 1, a qubit, that you don't know exactly the probabilities of this qubit, you cannot copy it. So a very smart guy, even back in the 60s, thought of, well, I can make money out of this. If I put a lot of qubits, say 20 qubits here on the right-hand side, I can make quantum banknotes. These cannot be forged, thanks to nature's own DRM. Pretty cool idea, and there's been a lot of work on this in the last few years. I have made a very small contribution. I thought about, well, can we combine this with a blockchain somehow? And I guess we can. I call it quantum Bitcoin. It's a paper that's available free online. Please break it, it will be a lot of fun. I want to make it better if that's the case. But I guess speaking about blockchains, this is from what I've heard, what you guys have been waiting for. How many of you listen to Secre's podcast? And I think a lot of guys do. Okay, so by chance, in January, I stumbled on a cryptocurrency, or maybe, I don't know if it's a cryptocurrency or not, something. They call themselves Quantum Walnut, and they say that they're quantum secure, like some kind of quantum physics mumbo jumbo, and they're gonna do money out of it. And I thought, hey, that's really interesting. Maybe there's some kind of new quantum currency or quantum blockchain somehow, I don't know. Let's have a look at it. And it's the weirdest ICO I've ever found. They have things like non-irreducible things. I mean, I read their white paper, and I was more confused by every page. They just techno-babble. They have these pictures of optical experiments, and just nothing had anything to do with doing things secure. I have a Twitter rant, by the way, on my Twitter page about this. So I asked them, hey guys, what are you up to? This is doesn't make any sense. Can you tell me more? And of course the response was, hey, please sign our NDA. I was like, no, I'm not going to want to sign an NDA because then I can't talk about it. I really want you guys to tell me, how does their system work? How is it quantum safe? How do you make money out of it? And they just refused. Sorry. So I went on Twitter and said, hey guys, you should really not invest in this stuff because it's just broken. They lie about their things. They have like this graph in the white paper. Oh, we compare a pseudo-random number generator to our system, and obviously you can see that our system is a lot better than a random number generator. And it's like, that's a really crappy random number generator you've got on the left there. I mean, we have pretty good pseudo-random number generators today, and this is not a good pseudo-random number generator. Well, also, even though you're saying that you should have a quantum random number generator, this is also old news. For instance, Quantic is a Swiss company, has made their quantum random number generator since 2001. It's not like this is a new stuff. So basically they have an optical experiment inside this box. They send photons and they split the photon in two, and then from quantum phenomena you can be pretty sure that it's random and good. But this is old stuff. And did they respond? Did they give me any answers? Did they tell me how this works? Did they give anything reasonable? No, the day after they said that we want to bring certain facts to the light regarding Jonathan Jogenfors. He's in the business of creating a product directly competing with ours, quantum Bitcoin. I was like, okay, I published a paper on something. That doesn't mean I'm a competitor. I just happen to know a thing or two about this field. So they never answered me about anything. Instead, they sent legal threats to my employer. Cease and desist. Okay, I did call them a scam at one point. Probably that's a bad idea, because saying that someone is a scammer means that I'm saying that someone is a criminal. So I have retracted my statements of them being a scam. And they think that I've complied with the cease and desist. But, I mean, I tweet as a regular individual. I'm a private person on Twitter. They sent letters to my employer, which is pretty bad. But I love our legal team. Basically, our university legal team said, oh, we cannot control what our researchers are saying. This is perfectly fine. And for some reason in Sweden, you cannot, I don't even know the English words, but förtal cannot be done against a company. Second? Slander. So one of them is in writing, one of them is verbal. I never know which is which. Slander or... Written slander. Thank you. Anyway, for some reason you cannot even do this against a company in Sweden. So I guess our legal team says it's fine anyway, but I don't know. This is a really, really weird ICO. I dig some more. I do some more searching into them because, I mean, now the gloves came off. They sent legal threats to my employer. I have no qualms about finding out their dirty secrets anymore. So they buy fake social media followers. They pay people to retweet and like their Twitter feeds. They pay people to go on forums and talk about them. And they're even stupid enough to put it all in a public Google Sheet spreadsheets. Who has done what and how much we're paying them. Even worse, it seems like, okay, I haven't confirmed this, but I checked the forum today, and people are not getting paid for shilling for them even, so they're doing it really badly, I guess. Some guys in the forums are complaining they haven't been paid. I can't vouch for whether that's true or not, but it seems to be pretty strange. And then, of course, they have totally unrealistic goals. I mean, I've not even understood how they're going to make anything work. And they say that in 2019 we're going to have 2% of the VPN market globally. I don't really follow here. But I guess they have an ICO. They want people to buy it. Can you guess how many percent of their goal they reached in their ICO? Remember, in ICOs, people are paid billions of dollars apparently. But they just reached like 0.5% of their goal on their ICO. I think they're pretty mad at me for sort of calling them out. I guess they didn't intend of finding someone with a PhD in quantum cryptography to find the white papers and start dissecting it. I guess that was not part of their plan.
Good work.
Thank you. So I guess I have pretty much time left. I was having a slide here, what I didn't have time for. I guess I do have some time for it. So how many of you guys have heard about IOTA? Some of you guys. So I'm not going to go into detail about this, but because why use proven cryptography when you can just roll your own? I guess we guys always say don't roll your own crypto, but the problem in crypto now is that crypto doesn't mean cryptography anymore. Some people say it means cryptocurrency. And when they hear do not roll your own crypto, they think it means do not roll your own cryptocurrency, which of course is a really weird thing to say. But the point we're trying to make is don't roll your own cryptography. You will have problems. And of course they rolled their own hash function. They didn't use like Ketchak or SHA-3 or something proven. Instead they wrote something on their own, and of course they had collisions. I mean, researchers at MIT found it pretty quickly. But why say thanks for a vulnerability report by good crypto researchers when you instead can accuse said researchers of bias? So there's such a toxic community. I've never seen anything like it. I think it's good tech in the beginning. I think blockchains are quite bad for many technical reasons, and these guys are making something new, which is great. I'm getting more and more into becoming a blockchain skeptic. And these guys are not using a blockchain. I like it. But why do these strange crypto things when you can just use good crypto instead? And they accuse these researchers of bias and conflicts of interests, and it's really bad. And again, IOTA, why not use a quantum safe signature, even though it requires users never to reuse addresses? You know, in Bitcoin, you can publish a Bitcoin address and have people donate to you many times. So you can take money out of your Bitcoin account and put it in somewhere else, and people can still send you money, and it's going to be secure and safe. Here, they decided to use a quantum safe signature scheme, even though taking money out of this wallet will expose your private key. That's just because how the signature scheme works. Internet signatures are based on Lamport signatures, and they cannot be reused, basically. In my opinion, yes, quantum computers are on the way. They will break our crypto systems, that's for sure. We need to take care of this into our security models. It doesn't mean that it's a problem today. It doesn't mean that we should drop everything else and just focus on quantum safety. It feels like all the new cryptocurrencies and ICOs are just saying quantum safe all the time. But there are harder problems to face, I think, than quantum safety. And last, but absolutely not the least problem for me with IOTA, but this is more of a subjective thing. Because why use binary when you instead can code in trinary? Yes, I'm not joking. IOTA is actually coding their system in trinary, not using ones and zeros, but ones and zeros and twos. Well, I guess it's up to them, but I'm not going to be very happy about it. Okay, I guess we're reaching the end of this talk. Quantum computers are far away, but as I said, we must update our security models to take them into account. It might be that someone will have a working quantum computer tomorrow. We don't know. It is possible that we can make quantum key distribution. That will be unbreakable in theory. But in practice, I'm probably going to be able to hack it, so don't use quantum key distribution. PostQuantum crypto, all this new fancy stuff with lattice-based crypto and code-based crypto, and isogeny based on elliptic curves. Still a few years out, the jury's out on this, but it's really, really hard to make quantum-safe cryptography. NIST even says it themselves. AES and SHA-3, those competitions were easy compared to this competition, because it's mathematically very difficult to make good quantum safe cryptography. And of course, please, crypto means cryptography, nothing else. And I guess I'm going to end it as the same way as the previous talk here. Should I invest in insert ICO here? No, I think you shouldn't. Okay, I guess that's all I have to say for today. Thank you much for listening, and thank you for having me here. Yes, some questions?
Well, if no one has any questions, I would like to thank you again for coming here.
Well, sorry, Jonathan, what was this rule about the 50% has to be discarded when
Yes.
you're working with
Okay, so I didn't go into much detail about why the system needs to, the ransom-based system I talked about, the system that we hacked. That one needs to discard 50% of the events, because otherwise it won't have quantum interference. It won't even be a quantum system at all. There's some kind of muddy, dark technical details of why this is the case, but it's very exploitable. That's the point.
Follow up on that question. That was the time-based system or
Yes.
polarization? Because
Exactly. The system that we broke was the one that did not use polarization. And the idea is that system will be easier to implement, less moving parts, you don't need expensive control equipment to control polarization stuff. Instead, time is much more robust against noise. That's the short version.
I'm just going to ask again, is there any more questions?
Otherwise,
That's
we can
fine.
have a discussion afterwards if people are interested in